Hello, this is Tracy. Welcome back, Math 135. We are continuing on in section 4.3. We are going to, again, decide, do we have a binomial experiment? And if so, what are all the bits and pieces? What are all of the notations that we talked about for a binomial experiment? So here's our experiment. Engineers define reliability as the probability that an item will perform its function under specific conditions for a specific period of time. For example, and this is an old example from an old stats textbook, so this data may not be current at all, so don't worry about it if, grandma has a heart replacement valve, because this may not be accurate. But back in the day when this stats book was written, replacement heart valves have probability of 0.77 of performing well for 15 years. We assume heart valve performance is independent. Whether one fails or not doesn't impact whether another one fails or not. We have a number of patients in a group of 500 who need another valve replacement within 15 years. What is the correct notation for the probability of at least 100 patients needing another replacement within 15 years? So go ahead, read that again if you need to. Pause the recording. What we're going to do now is decide, is this a binomial experiment? So we have three conditions to decide if an experiment's binomial. 1, do we have a fixed number of trials? Now remember, I said trials can be something like how many times you flip a coin or roll a die and count your number of ones. It can also be the number of patients or subjects. So in this case, we are looking at 500 patients. Yes, n equals 500. So we have a fixed number of trials where the number of trials is the number of subjects. 2, each trial has to have 2 outcomes, either success or failure. So a success is, what is it we're counting? So we want to count the number of patients who need another valve replacement within 15 years. So success is need a valve within 15 years. So, like I said in the last video, a success in these types of experiments isn't necessarily a good thing. We're counting, our success is whatever it is we're counting. If we're counting the number of valve replacements, that's a success, even though it's not a very happy outcome for getting your valve replacement. What would a failure be? A failure is don't need that valve within 15 years. Valve within 15 years. So yes, 2 outcomes. And number 3 is our trials are independent. Sometimes you wouldn't know that unless somebody tells you the assumption. We assume heart valve performance is independent. Because that assumption's being made, yeah, we are going to call these trials independent. So yes, this is a binomial experiment. Yes, this is a binomial experiment. Now what we want to do is we want to figure out all that notation stuff that we were looking at in the last video. So we want to, well, first of all, we have to decide what our random variable is. So our random variable x is whatever it is we're counting. So this is the number of valves replaced within 15 years in our group of 500 patients. How many of these valve replacement patients need another valve within 15 years? And what value can this random variable take on? Well, maybe nobody needs a replacement, or one person does, or two, or all the way up to the full 500 that are in this study. What is the probability of a success? And remember, for us, success is probability of success, probability that we need a valve within 15 years. Now, I know, common thing everybody wants to do. Everybody wants to come up here and say, ooh, look at this. Oh, come on, get my cursor, my little pen up there. This is 0.77. But this 0.77 is telling us that's the probability of performing well. Performing well. In other words, not being replaced. So this would be our Q. Q equals 0.77. In our study, even though that's the good outcome, it's a failure because that's not what we're counting. So to figure out our P, our probability of success, our probability of needing that heart replacement valve, P is 1 minus Q, or 0.23. So P is 0.23. Now we put all that together and we can get our notation. X is a random variable that follows a binomial distribution with 500 trials and probability of success 0.23 on any given trial. Now, let's figure out our expected value. And remember, our expected value, mu, is the expected value for the number of valves needing to be replaced, within 15 years. If we took a whole bunch of groups of 500 patients, on average, in those groups of 500, how many are going to need their valves replaced? Well, 500 times the probability of needing a valve replacement. 500 times 0.23. That's going to be 115 valves in that group of 500 that we expect to need replacement. Our standard deviation, the square root of, again, NPQ. Remember that formula. In this case, N is 500, P is 0.23, Q is up here, is 0.77. Don't forget we're taking the square root of it. Pop this into the calculator the same way we did before, and we're going to wind up with a standard deviation of about 9.4 valves. So again, we're just writing the notation, so we have all the bits and pieces for this binomial experiment. And then what we're going to do is we're going to calculate probabilities off of it. But for now, we just want to get our notation down. So remember, we want the notation for the probability that at least 100 valves need replacing within that 15 years. And that's going to be the probability that our random variable x takes on values greater than or equal to 100. So again, that's just a notation thing. So we're going to take a look at another one before we start diving into crazy calculations. Is the given experiment binomial? If so, identify all that stuff, blah, blah, blah. So we roll a 6-sided die, and we count the number of rolls it takes us before we roll a 5. We roll a 6-sided die and count the number of rolls it takes us before we roll a 5. So, does this experiment have a fixed number of trials? We're going to go through those 3 different criteria for a binomial experiment. Well, we're rolling a six-sided die. How many times are we doing it? We don't know. We count the number of rolls it takes to get a 5. No, we don't have a fixed number of trials. This is not a binomial experiment. Alrighty, I'm going to stop this recording and we will continue our 4.2 lecture in the next video.